Okay, let's start. Welcome everyone. And today we are happy to have a talk by Mikhail Shaposhnikov, and he will speak about anomaly-free scale symmetry and gravity. Please start.
Okay, thank you very much. And, hello everybody. So I'm going to talk here about anomaly-free scale symmetry and gravity. And my talk is based mainly on the paper which Anna Topra and myself had this year in January, but with inputs from quite a number of other papers which was done in collaboration with Georgios Karananas, Vladimir Kazakov, and then many people listed here. Okay, so I will start from reminding you what conformal symmetry is, what is spontaneously broken conformal symmetry, and then I will come to the question how conformal symmetry interacts with gravity. So we are going to discuss wild anomaly, and then anomaly-free scale symmetry. Finally, I will talk a little bit about scale symmetry and phenomenology, and then I'll come to conclusions. Okay, so it's kind of well known that Maxwell equations, very, very old Maxwell equations, is a profound source of different symmetries which we use in particle physics and which are the symmetry of nature. Okay, if, for instance, if we look at three Maxwell equations, which are written here, where F mu is the Maxwell tensor, we can ask the question, what kind of transformations we can make so that the Maxwell equation stays invariant and do not change. Okay, and everybody knows that the study of Maxwell equation led to discovery of Lorentz and Poincare transformations of Minkowski spacetime. So if we make a transformation where four vectors corresponding to time and three spatial symmetries are changed in this way, so that shift, which tells us that the space is homogeneous, and then there is a Lorentz transformation which is made here with the Lorentz matrix, which obeys certain properties. So Maxwell equations are invariant. So the group corresponding to these transformations is a Poincare group with 10 parameters having 4 translations, 3 rotations, and 3 boosts. So in fact, soon after the Poincare symmetry was discovered, Bateman and Guggenheim found that if you look at the Maxwell equations, then you find out that the group which leaves these equations invariant is actually wider. It's not just a Lorentz group, it's the group which can be written as SO P2, and this group, in addition to translations, in addition to Lorentz transformation, it has 5 extra generators. One of them corresponds to the scale transformation. So what you do, you multiply the x mu by some arbitrary factor lambda, and there are 4 special conformal transformations. So what is written here are actually infinitesimal transformations. Okay, and here A is an arbitrary forget. Okay, so how can we visually represent this new transformations which be here? So the scale transformation, they are basically stretches the distances. So if you have a square like that, you apply to it a scale transformation, then you get the same picture, though the distances between, say, these 2 points will be different. The conformal transformations are some more sophisticated. The main property of them is that if you have some lines which here intersect, and when you apply the conformal transformation, then the angle of intersection doesn't change. So this picture goes into this type of the picture. Okay, so mathematically, we can ask the question: what is the form of what are the main properties of this conformal transformation? So for this end, we can consider the Jacobian of the transformation, and then the Jacobian transformation. It's almost like a Lorentz transformation. So for Lorentz transformation, the Jacobian would be just our Lorentz matrix lambda, but now this Lorentz matrix lambda is multiplied by some function of coordinates. Okay, and so this means that the metric transforms as follows. So initially, so if you start with the metric of the flat Minkowski space-time, it mu, when we make the conformal transformation, then we get the method which is still proportional to eta mu, but it contains some factor in front. So this factor, for instance, for dilatations would be just the overall scale factor lambda, whereas for special conformal transformations, it is given by some specific function of x, which is written here. Again, A is an arbitrary arbitrary forget. Okay, so since we got new kind of symmetry, we can ask ourselves whether one can construct conformal field theories. Okay, so what would be the conformal field theories? These are the quantum theories which are invariant with respect to conformal transformations. Okay, so if you take some fields, primary field with some spin S, then this field will transform in the following way under conformal transformation. Okay, so first of all, there is this matrix here, which is just representation of the Lorentz group. Okay, so if we were making Lorentz transformation, then this factor would be absent. Now, what we get here in front is this exactly this function b, which appears in the change of the metric, and this function b comes with some power delta, and this power delta is called the scale dimension of the field. Okay, so what is interesting and also what is important for conformal transformation, so if you write an action which is invariant with respect to conformal group, then this the scale invariance part of conformal group actually forbids the presence of many dimensional full parameters in the field. So there are no scales, there are no exceptional length, nothing like that. Okay, so why conformal field theories are interesting? Well, they're interesting because conformal symmetry restricts the form of different correlation functions. Okay, then it happens that conformal field theories are a very important tool to look at the behavior of many systems in the vicinity of critical points associated with phase transition. So they have not only scale invariance, but conformal invariance close to the point where we have some statistical system, the second order phase transition. And also, conformal field theories describe the limiting behavior of different quantum field theories deeply in the UV region or infrared domains of energy. So, for instance, if you take QCD and consider asymptotically high energies, then QCD happens to be a free field theory because of asymptotic freedom. The free field theory is conformally invariant. So the question arises: okay, the Poincare symmetry, as you know, plays a very important role in physics. Okay, the conformal group follows from the study of Maxwell equation. We can ask the question: could it be that conformal field theories are even more important, and that the ultimate theory of nature is conformal? So why this question? So in fact, if we impose conformal symmetry, scale symmetry on different theories, we are getting several benefits. First, the CFT are finite theories, so they don't contain infinities. Now, on more phenomenological footing, if you take the standard model, Lagrangian of the standard model, and put the mass of the Higgs field in this theory to 0, then you will find out that, that at the classical level, classically, this theory enjoys the complete conformity. Okay, we know that the mass of the Higgs boson is much smaller than another scale of nature, which is the Planck scale. So maybe the smallness is associated somehow with conformity. Yet another interesting observation is that the energy of the ground state in conformal field theories is equal to 0. It's actually easy to understand. It doesn't contain any scales, and the energy has certain dimension, energy density G to the fourth, so we get 0. We also know from observations that the vacuum energy in our universe is a tiny number in comparison with any other scale which has, like electron mass or Planck scale or electrolytic scale. So could it be that the conformal symmetry stays behind the smallness of the cosmological concept? So, I mean, if you look at that more closely, then there are several challenges which come immediately to mind. So, as I just said, conformal invariance forbids the presence of any dimensional full parameters in the action of CFT. Moreover, if you look at conformal field theories, you realize that conformal theories do not have any well-defined particle space. So these are mainly distributions what we have here. And this is in the drastic contrast with nature, because first of all, in nature, we have different energy scales, scale of quantum gravity or Newtonian constant, Planck scale, they're large, 10 to the 18 GeV, Fermi scale, cosmological constant, and all these things are dimensional full numbers. And also, of course, in nature, we have well-defined particle states like electron, proton, whatever. These are cannot be the states of conformal field theory. Yet another challenge is that the conformal symmetry is defined in flat space-time, whereas the ultimate theory must include gravity and arbitrary method. And in fact, I will discuss that later as well. The natural generalization of conformal symmetry of flat space-time to curved space-time is the Wild symmetry. And Wild symmetry is known to be anomalous if quantum corrections are taken into account. So how to deal with it? Okay, so one challenge is the absence of scale, another challenge is anomaly. And so let me go first through the challenge which is associated with the presence of scales in nature and absence of scales in conformal field theory. Well, you know very well that if you have some global symmetry, then this global symmetry can be broken spontaneously, and so it becomes hidden. Okay? What happens there is that Lagrangian of the theory is invariant with respect to this or that theory, but the ground state is not. The elementary example here is U1 global theory. Is U1 global symmetry, theory of single complex scalar fields. So if you look at this theory in symmetric phase, so symmetric phase is the phase in which the ground state is also symmetric, also doesn't change if you apply the symmetry transformation, then you will see that the spectrum of this theory contains scalar particle. These 2 degrees of freedom correspond to the global charge. But now this symmetry can also be spontaneously broken. This would happen if this scalar field has non-zero vacuum expectation value, and this happens if the interactions, self-interaction of this scalar boson has a particular form. Okay, so in the case of the broken symmetry, then the spectrum changes drastically. It contains a massive neutron particle and massless scalar particle that is so boson that the number of degrees of freedom remains the same. So can we go along these lines and get a theory with the hidden conformal invariance, so that the conformal invariance is exact at the Lagrangian level, but the ground state is not. And so the answer to this question is positive, and the toy model, which represents all that, is written here. So imagine that we have 2 scalar fields, H and high. So I will be calling H the Higgs field, which can be really the Higgs field of the centered model, and field high I will be calling the Dilatations. Okay, so let's take this theory. This is the most general Lagrangian, which you can write, the 4th power, which contains 4 powers of the field, and it's analytic with respect to different fields. Okay, so these are kinetic terms for field H and high, and this is the potential for these fields. And note that there are no any dimensional free parameters like masses in this field. Okay, and then this potential depends on three different couplings, lambda, alpha, and beta, and as specific. So this theory here, again at the classical level, I will be discussing quantum corrections a little bit later. So at the classical level, this theory is invariant with respect to the whole group of conformal transformation with 15 parameters. Okay, so a specific choice of this couplings, lambda, alpha, and beta, actually leads to the situation when we have spontaneous breaking of the conformal symmetry. So these terms were grouped in some particular way, so that you can see immediately that the question about whether conformal invariance is spontaneously broken or not is boiled down to this coefficient beta, which stands in front of pi to the 4th. So if beta is greater than 0, then this theory has a unique vacuum in which I is equal to 0, H is equal to 0, and this is theory which is completely conformal invariant, no scales, no particle excitation. Okay. So if you take beta smaller than 0 here, then this theory doesn't have a ground state, so it's unstable. We don't like to consider this type of theories. And then if this guy beta is equal to 0, then you find that the vacuum is degenerate. So there are many states, and all the states are lined along this line, where this guy in brackets is equal to 0. And if you pick up the state in which vacuum expectation value, say pi, is not equal to 0, you find out that yes, this symmetry is spontaneously broken. You get well-defined notion of particles, and in this case, you will get one massive particle, the boson, and one massless particle, the dilatation. And this can be shown on this picture, on this figure. This is the case of internal symmetry, U1 symmetry. These are two directions, phi1 and phi2, real part of phi, imaginary part of phi. This corresponds to the unbroken U1 symmetry, and then this circle here represents the set of ground state that is spontaneously broken U1 symmetry. Now, if you look at the scale symmetry, if beta is greater than 0, the ground state is unique. If beta is less than 0, then there is a direction along which the potential is not bounded from below. And if you take beta is equal to 0, so there are directions where flat direction in effective potential, which corresponds to the breaking of conformal invariance. Okay, and this toy model, it can be generalized right away to the case of standard model. If we want to talk about phenomenology, what we can do, just take the Lagrangian or the standard model, put their mass of the Higgs boson equal to 0, and introduce the same type of potential which I discussed on the previous slide. And here the phi field corresponds to the Higgs boson. Take again the self-coupling of dilaton in this form equal to 0, equal to 0, and that's it. Okay, you get phenomenological acceptable theory. So I will talk about that later as well. which has the same particle spectrum and has the standard model plus extra particle masses dilaton. Okay, so in order to make this theory phenomenologically acceptable, we need to have this parameter alpha, which basically tells you what is the interaction between the Higgs boson and the dilaton sufficiently small so that this particle is seen, and this happens when the vacuum expectation value of the dilaton field is much larger than the Fermi scale, much larger than the electrons. Okay, so what I was talking about is the classical picture. So we see that if we don't care yet about quantum corrections, then by breaking the conformal symmetry spontaneously, we can introduce the scales. All scales which we observe in nature will be proportional to the dilaton wave, and but we still keep the conformal symmetry intact at the level of all interactions. Okay, so the question arises, this of the classical discussion, what is going to happen if we add quantum physics in that. And here, at first sight, the trouble comes because once we have quantum field theory, there are all sorts of divergences there. All these divergences should be subtracted in some way, but if we use the traditional methods, standard methods for subtraction of these divergences, then you introduce in this or some other way different scales. So, for instance, if you are regularizing your divergent expression with the help of the UV cutoff, then this UV cutoff is kind of large number, which is a scale, and since you introduce the scale, you break the scale symmetry and conformal invariance immediately. So Coleman used to say any regularization procedure breaks the scale symmetry in a strong way, and so this symmetry cannot be kept. The same happens if you do Pauli-Villard's regularization. The same happens if you use dimensional regularization, where you introduce a parameter mu, which is needed to match the four-dimensional quantities to n-dimensional quantities. Okay, and all the scales break conformal symmetry, and so it seems that conformal symmetry dies when quantum physics is at the point. Okay, so in fact this is not true. Okay? There is no problem to keep the conformal symmetry intact in all orders of perturbation theory. And the idea behind is that simply use say the cutoff scale proportional to the dilaton field, or keep the tooth parameter of dimensional regularization proportional to this scale. And if you do it in this way, you can remove the divergences from this theory in such a way that explicit scale doesn't exist. Okay, and so that the resulting theory is scale invariant and conformal invariant in all orders of perturbation theory. There is a certain drawback in this procedure, which is that the resulting theory is not renormalizable. Okay, so the theory is renormalizable, and all divergences can be removed if you use the standard way of renormalization, say the cutoff or mu. Now, if mu is field dependent, we can show that there are that the new type of divergences appear at every step of your computation. This means that the resulting theory is conformal invariant, but not renormalized. Okay. Should we worry about that? I would say no, because of the following reason. The theory of nature and gravity, in particular, is not renormalizable in any way. Okay, so we have divergences in any theory of gravity. Now, all the normalizable terms which appear if you want to keep the theory conformal invariant, they are suppressed by dimensional full parameter, which is the dilaton depth. Okay, and if you take the dilaton depth of the order of the Planck scale, then this non-renormalizability, which appears here, is exactly on the same footing as the non-renormalizability, which appears due to derivation of interaction. Okay, so the theory which you construct in this way can be considered as an effective field theory, which is valid up to the energy scale fixed by the uniform depth. Okay, as I already said, this gravity is not normalizable in energy. Okay, so the message from this discussion is that there is a possibility, and there is actually no problem to have a theory which is conformally invariant, okay, at the quantum level. And the question arises, so what is this structure of this conformal theory in the low energy domain? Okay, and so in the low energy domain, our conformal theory contains just one degree of freedom. This is the dilaton field. Okay, so in principle, there are other massless fields in the standard model, such as the photon, but I'm going to disregard the existence of photon because it doesn't change the discussion is forward. Okay, so we can ask the question: what is the most general theory which is conformal invariant and which contains our massless degree of freedom ability? Okay, and this question can be analyzed systematically in the following way. So we have field high, and then to construct effective action, we can act on this field high by different number of derivatives. Okay, and so we can classify all the conformally invariant operators by the number of derivatives which show up in the action. Okay, so if there are no derivatives whatsoever, then there is just a unique operator in 4 dimensions, which is high to the 4. So the canonical dimension in field high is taken to be GD as it's normal for the scalar field. And then if you have 2 derivatives, then you find out that there is simply a kinetic term like this. Now, if you consider the operators with 4 derivatives, then you find out that there are 2 operators which respect conformal invariance. So if you would just acquire scale invariance, then the number of scale invariant operators with which contains 4 derivatives is 3. It's like 1 unit more, and this can be continued. The way how all these operators can be constructed with arbitrary number of boxes can be found in our paper, and some other books as well. But what will be important for us in what follows is just this part, which contains 4 derivatives. So basically a square of the box. All that will be related to the Weyl anomaly. Okay, so now, as I showed, the first challenge in identifying the conformal symmetry with the ultimate symmetry of nature can be overcome. Okay. We just take the conformal symmetry, which is spontaneous. So now let's come to the second challenge, which is associated with embedding the theory in a flat space-time in a more complicated setup in which we have the metric, the dynamical metric. Okay, so let's see what is the most natural generalization of conformal symmetry to the curved space-time. Okay, so what we can do, have arbitrary metric, we can potentially make arbitrary coordinate transformations, and we can consider the set of transformations which leave the metric, arbitrary metric invariant up to the conformal factor, which depends on x. Okay, so we make this transformation, which is a natural generalization of conformal symmetry. But since we can now do arbitrary coordinate transformation, we can actually undo this part of the transformation, and in this way we arrive to what is called Weyl transformation. So what you do, you change the metric to the metric, which is original metric times some arbitrary factor, which depends on position. Okay, so this is the Weyl symmetry. If you take arbitrary function, only the arbitrary function of space-time coordinates. Okay. And now we can ask ourselves whether we can construct the theory which is Weyl. Okay, and so the problem can be posed in the following way. We consider conformally invariant theory. Even we can take a frequent theory. Okay, then we couple this theory to gravity in a Weyl invariant way, and then we integrate out matter fields to get effective action for the metric. And here the anomaly comes. It happens that the normalized action is actually not Weyl invariant. Okay, so the conclusion is that Weyl symmetry therefore cannot be complete symmetry of nature. So perhaps this can be cured for a specific particle content of the theory, as was discussed a long time ago by Praktin and Saitlin, and there were some other suggestions recently. So the idea here is to prepare a specific particle content of the theory, and then this specific particle content, this anomaly disappears. So let me tell you how this anomaly can be understood almost without any computations whatsoever. Okay, so we can ask, there is the following method how to construct conformal invariant Lagrangians in the flat spacetime. Okay, as I told you already, this can be done in a so to say, brute force direct way. You just have your theory in flat space time, then you write down different terms, and then you do your conformal transformation, and then you keep only the terms which are invariant with respect to the conformal transformation. So the same program can be realized in a somewhat different way, which is presented at this slide. So what you can do, you can take an arbitrary action, which is invariant with respect to arbitrary coordinate transformations. Okay, so deep invariant action, and you take an action which contains metric content, no any other fields, so it's kind of pure gravity, but with all possible terms included. Then what you can do, you can take this action and replace the metric G mu by G mu times some scalar field, okay, chi square over n blank square. So after this replacement is made, then your theory visibly contains the metric and the scalar field, and by construction, this theory is while invariant with respect to this transformation. So you change the metric, and you undo this change modifying the scalar field phi. So you see that in this combination, this and that factor cancels away. Okay. So, for instance, this type of operator R will give you chi square R plus kinetic term for the scalar field. Now, if you take this theory and put it in a background which corresponds to Minkowski space-time, so that G mu is replaced by eta mu, then you automatically are getting a term which is conformal invariant in flat space-time. Okay? And what actually happens, and that's very interesting, that all operators and low energy dilaton theory in flat space-time can be derived in this way, except one. Okay, so there is one specific operator which you cannot construct by this method. Okay, and this means that this particular operator cannot be written in while invariant way in the presence of gravity. Okay, about gravity, and because of that, while symmetry cannot be exact symmetry of nature. So this, what is this troublesome operator? So why I was talking about the box square operators at the first place. Okay, so let's take all possible operators which contains 4 derivatives and which are in pure gravity. Okay, so then there are 4 operators of this type. This is scalar curvature square, and then this is I-log density. So I-log density is some particular combination of R square, R mu times R mu, and E-mod square. Then we have an operator which is while square, while W is the while tensor, and then we have a box of R. And now you see that if you make the transformation which I was talking about, this type of transformation, then what is happening with all these terms? So this guy is while invariant, so no non-trivial action for the scalar field can appear from it. The terms like E4 and box R, we don't care because these are the surface terms. And this means that only the operator R square gives a non-trivial result. Okay, so we can just get one conformally invariant operator by this method, but we know that there are two. Okay, and so this operator here is cannot be reproduced in a while invariant field. Okay, so it looks like that's the conjecture that the nature is conformally invariant is filled by graph. Okay, in fact, there is a potential flaw in this logic. It happened to be not the flaw at the end of the day, but still it looks to be a flaw in the logic. And this flaw is the following. If you talk about conformal symmetry in flat space-time, then this is a global symmetry with a finite number of generators. Okay, we have 15 generators. And if we talk about Weyl symmetry, then the Weyl symmetry is the local gauge symmetry with an infinite number of parameters characterizing the transformation. So there is perhaps a possibility that one can find out some subgroup of this Weyl symmetry, which is finite and which generates anomaly-free transformations, and which coincide with the conformal group of Minkowski space-time if the metric is taken to be fact. Okay, and so that's exactly the question which we're going to analyze now. Okay, so how can we proceed? The troublesome operator in flat space-time, which we cannot reproduce in gravity, because gravity is included, is this one. So it's a box square acting on this function. Okay. So if the dimensionality of space-time is not equal to 4, we can take a fractional dimension also. Then we can construct an operator which is precisely bilingual. Okay, and then this operator, that is the different forms of that. The most convenient for me would be the following. So this guy, box square, is replaced by operator which is called the Ribert operator because of some mysterious reasons, because it was found first by Satan, but then there is another contribution here containing box R, containing Eilert density. But what is most important for us is the term which exactly shows the origin of the Weyl anomaly. So this term, which is written here, anomaly, is the Eilert density divided by d minus 4. So when the number of dimensions goes into 4, and then this term explodes. Okay, so incidentally, similar things happen if you consider other dimensions. So, for instance, if you consider all types of even dimensions, 6, 8, etc., then there is also the same structure of anomaly. So you have full divergence in the corresponding space-time. So in 6-dimensional space-time, 8-dimensional space-time divided by this factor d minus 4. Okay, so what is the role of this part? The role of this part is that when we make a Weyl transformation of this term, then this guy is changed in this way. Okay, so the change of this anomaly term is finite when d is going to 4. I can take exactly at this form. And one can show that there is no way to construct a local operator in d equal to 4 with the transformation properties of this type. one can construct non-local transformations, but local transformations do not exist. And so our question about the subgroup of the viral group boils down to the following. We make a change, we make the transformation, viral transformation of this anomaly term, which is here, can define omega, non-trivial omega, which are such that this guy is a surface integral. Okay, and then if this is a surface integral, then we don't care. Then the anomaly is not there. Okay, so it's more or less straightforward to find the answer to this question. What one can do, one can look at that part and consider the variation of this part with respect to the method. Okay, and require that the variation of this part with respect to the method is equal to 0. So if this is true, then this part will not contribute to the equation. Okay, so this can be done. The variation of this term with respect to the metric, it contains change of the metric, new calculation of the metric, some operator which can be found explicitly, and then this is multiplied by the second covariant derivative of parameter omega of conformal transformation. Okay. So if the variation of metric is arbitrarily small, and if the metric is arbitrary, then this is equal to 0 if and only if this second derivative of omega is equal to 0. But for arbitrary metric, this can only be true if omega is equal to constant. Okay, so this basically means that the only if you have a curved space-time, then the only possible wild transformation, which is anomaly-free, is that corresponding to the scale transformation. So there is nothing left. Okay, if you take this equation and solve it for the flat space-time, you find out that there are other transformations which exactly correspond to special conformal transformation. Okay, so why the solution here is unique? So that can be found in a pretty much direct way. You take this guy, then you apply to it the covariant derivative and consider the commutator of covariant derivatives, which gives you a Riemann tensor. You can construct a couple of indices, so it follows that the reach times this derivative must be equal to 0. And if you consider the space the nature of the reach tensor, then you find that omega is equal to the constant. So what we have is that gravity does destroy the conformal symmetry down to scale. Okay, so let me briefly describe the consequences of that. Okay, so first I was talking about the standard model in the flat space-time. So standard model in the flat space-time can be conformally invariant. Now, if we add gravity, then what the theory which we should consider is the theory which has the scale invariance. Okay. So this is the lowest order Lagrangian would have this form, the second derivatives only, this term we discussed, this term we discussed, and this is the coupling of the dilaton to R. And so, looking at this section, you can see immediately that scale invariance is better than violent invariance. It's better than violent invariance in the following sense. If you would require violent invariance here, then this parameter zeta would have a specific value. Zeta is equal to minus 1/6. Now, here, this parameter is arbitrary, and this means that the Planck scale can be dynamically generated when the scale symmetry is spontaneously born. Okay. This factor minus 1/6, if you insert it here, would produce the wrong sign for the Planck scale. So you can also live with that, but then you have to show the sign effect. Another interesting phenomenological application of the coupling of the dilaton to gravity is that the dilaton in this configuration has only derivative couplings to matter, and that does not lead to any long-range fifth form. So if gravity were absent, then the dilaton field would transmit long-range forces. 1 over r square behavior. Now, if the dilaton is coupled with gravity, if everything is still invariance, this is not the case. Okay. So another phenomenological requirement here is that this self-coupling of dilaton, which is appearing here, must be extremely small, because in fact, because this term, which gives rise to the cosmological constant. So the way to see it is to go from this action to the Einstein frame. So this action is written in so-called Jordan. Okay. So if we talk about four-dimensional, four-derivative action, interaction of the dilaton with gravity, then you can basically write all sorts of scale invariant terms here. The terms which are shown here have the conformal invariant counterpart in the flat space-time, whereas these terms are only scale invariant. Would be expected to be suppressed by the Planck scale, and this is not necessarily true for this constants here, which depend on the mass scale in something different. And I think that at the end, so here is a proposal for scale invariant theory, which can lead to phenomenology consistent with all experiments which are currently available. So this is the theory which contains particles of the Sanders model, graviton, which I already discussed, the dilaton, which I already discussed, plus 3 Majorana leptons. And why do we need 3 Majorana leptons? We need them to solve the problem of neutrino masses, and also the problem of their symmetry of the universe. So these particles can be added to theory, and then this is a theory which, first of all, agrees with all experiments. The dilaton field gives masses to all sorts of particles, determine the Planck's field, gives mass to the Higgs boson, gives mass to around electrons. Higgs boson itself gives masses to fermion vector bosons, provide inflation, and as I mentioned, the Majorana electrons give masses to neutrinos, that matter integrate, provide that matter integrate, and relate to invariance symmetry. So I'm closing, saying that the global scale symmetry is the only anomaly-free extension of the conformal symmetry of flat space-time. Curved space-time, well, perhaps the word extension is not good because it's symmetry which is smaller than conformal symmetry. This symmetry can be kept at the quantum level if dynamical gravity is present. And if the symmetry is spontaneously broken, then its whole this type of theory is consistent with all available experiments and populations, and thus can play a role as the global symmetry of nature. There are several challenges which should be solved here. So one of them is the reason for existence of flat direction, and this is closely related to the cosmological constant problem. And so within what I said, it's absolutely unclear why the corresponding direction should exist and why the cosmological constant should be small. And of course, yet another challenge, this is a challenge common to any theory with gravity, is what is UV completion, how we can solve this theory, what happens in this theory at very large energy scale, which is larger than the dilaton graph, this is larger than the. So thank you very much for your attention.
Thank you. Are there any questions?
What about the unitarity of such kind of theories?
Yeah,
you have high derivatives and all that.
Well, these theories are considered as effective field theories. So that energies which are much smaller than the okay, so these terms with the higher derivatives have to be considered as perturbation. Okay, so as in any type of effective field theory. So you keep the same number of degrees of freedom which were in your original theory, and consider these guys as perturbation. Okay, and when your energy is much smaller than the dilaton there in this case, okay, then everything is fine. Okay, so the theory is unitary, all corrections are computable, and now when the energy which you're interested in is comparable or larger than the dilaton web or the Planck scale, then you're in trouble because the perturbation theory doesn't work, or the amplitude, the diversion of energy, and it's not clear what's happening. Okay? Situation. I would say it's literally the same as you have a many theory of that.
Okay, thank you.
Dima? Dima Levkov?
Good day, associate. Sorry. Do you hear me?
Yes. And now we don't hear you.
I don't hear you, Dima.
Do you hear? Okay. Can I ask wrong?
Sorry, I didn't get your question.
Okay.
I have a question. In your discussion of which operators how you construct conformal invariant operators, you're kind of assuming locality.
Yes, that's correct.
Because in principle, if you relax locality, you can have many more options, I guess.
Yeah, this is certainly true.
Yeah, the reason for there was a suggestion in 70s by Fratkin and Vilkavisky about trying to sort of also avoid conformal anomalies by essentially using non-local construction of the constructing conformal factor of the metric out of the metric as a non-local operator, and then using it to sort of as a regularization effectively. So that also formally resolves conformal anomaly, but it introduces all sorts of non-localities.
Yeah, this is certainly true.
So that's in principle is not clear how that could be made to work. But then another sort of vague question which I have, I think what you are trying to do is to argue for a difference of avoiding conformal anomaly by introducing an extra scalar compared to, say, axial anomaly or chiral anomaly. For chiral anomaly, you can also introduce an extra degree of freedom. In fact, like Fadeev and Chitashvili were trying to do. And then again, you may find problems with unitarity, for example. And again, the question is whether you can formulate this consistently in effective field theory approach, and what would be the scale. Yeah, that would be a major problem, probably.
Yeah, well, okay, I do know about this attempt to make a chiral anomaly with some extra scalar field, but it doesn't seem to me that this question was solved in a way that some consistency was constructed. So here, my logic is that is the following. So it looks to me that okay, so conformal, the global conformal symmetry of flat space of time is kind of very nice symmetry. It's wider than Poincare group, and also it's okay. As I said, there are some nice features about that: small Higgs mass, small cosmological constant, absence of divergences, etc., etc. But then, when you think whether this can meet phenomenology, okay, then you must say that this symmetry is spontaneously broken. And once you say that this symmetry is spontaneously broken, the only way to achieve that is to have an extra degree of freedom, which is the dilatation. Okay, and then if I'm doing that in flat space time, then the action for the dilaton it should be local, okay, at least in these theories which we consider. And so this was the main argument why we are looking for locality. Okay, and yeah, I mean, I know that non-local actions also were studied quite intensively by Emil Motula and others, Ignatius and many others, different neurological applications where they were introducing non-local action coming from anomaly, but also I don't think that this study was how do they put that? Absolutely convincingly leading to some interesting stuff. But yes, that's an interesting direction.
May I ask one more question? What about the vacuum expectation values of various composite operators which exist in the quantum field theory?
Yes.
Can you reproduce them through this mechanism?
I'm not sure I understand the question.
Composite operators, say in QCD, have non-zero vacuum expectation values, also giving some scale parameters. So can you model them in this effective way?
Yeah, sure, of course. So if let's forget about gravity, okay, then what you find out that lambda QCD is just factor times left of the dilaton field. So all and this factor in front is basically exponential minus 1 over a strong Kaplan constant taken some energy scale. So all composite operators like in QCD or whatever, they are reproduced, simply replace, I mean, the averages of these composite operators, say in Maxwell's QCD, they would be proportional to the lambda QCD to the corresponding power.
Okay, so once you reproduce lambda, you reproduce everything.
Yeah, once you reproduce lambda, you reproduce everything.
But that would mean that somehow you need to, what this boils down to is a prescription, UV regularization prescription, which you need to specify for everything, including QCD, whatever.
Yes.
So ideally, it should come from some consistent UV consistent theory where you have your dilaton already.
Yes, in principle, yes, but say this type of relation which I was talking about, that lambda is related to the dilaton left, this you can find even without knowing the completion. This is basically straightforward because the way to find these relationships is the following. So the main trick here, let's take the dimensional regularization for simplicity. The main trick here is that you take the two parameter mu is equal to this field, okay? And then you do your computation and you literally see how the normal running of the couplings is reproduced, and that the parameters which appear due to dimensional transmutation in normal counting, how they are related to the dilaton value.
Okay, there is one more question from the chat. I'm not sure that I understand it. So the question is the action compatible with dilatonic black hole solutions?
With what?
Dilatonic black hole solutions.
I'm not sure I understand the question.
Okay, so We can ask for
no, I don't understand. I can imagine that.
Yeah, okay. I don't see any clarifications. Okay, so does the action admit black hole solutions?
Yeah, sure. Yeah, well, because this is a normal gravity. Okay, put all the fields put dilaton field to the vacuum expectation value. Okay, and in this way you get pure gravity, and then pure gravity admits black hole solution, and that's it. And all other fields put to zero. Okay, so dilaton is just equal to the left. Then what we get is pure gravity. The pure gravity is a black hole solution. Yes, answer is yes.
Okay, are there any further questions? Okay, if not, then thank you very much for a nice talk.